first off talking about what is system architecture and why it's important, why we study it at this early stage, what concerns are involved in architectural design, standard architectural patterns that are used. We'll talk about why it's important to look at these, and then some examples of particular application architectures. Okay, so first of all, what is architecture, particularly system architecture? It's a high-level design of the system determined by both external constraints, so most commonly compatibility with other systems, whether they are computer systems or just organizational systems in which it's going to be situated. User concerns, data security is a big one, and related to that is multi-user access, so credentials for different users and access permissions for different users, which parts of the system they can access, that sort of thing. And then the logical design. So the software packages that are involved, you might be building a system that's actually made up of, logically, lots of different parts. And so that goes into your architectural design and the subsystems that you're using within it. The systems architecture is driven by your hardware or physical constraints. So this is talking about the actual platforms on which you're going to be hosting your system, or the devices that are going to be used to connect to it, that type of thing. So that's the systems architecture. The software architecture is the software, obviously, and it's driven more by the logical representation of the software that you're building. So the software platforms that you're using, the packages, the subsystems within it, and it's going to be influenced by the systems architecture. So if you have a distributed system, your software is likely to be distributed as well. Right? So why do we think about software architecture? Why is it so important? When we talked about agile software development, we talked about the idea that you're constantly refactoring things, redesigning things to make it better, to make it stronger, and that sort of thing. The problem with the architecture level is that it's actually very expensive to refactor this, because refactoring the organization of the software is going to affect every little bit of the software. And so you have to redesign every single little thing. Whereas if you get the architectural design right from an early stage, then when you're refactoring, you'll be focusing on the subsystems within it and only refactoring smaller bits, which will be less expensive, because you'll have a clearly defined interface between that system that you're refactoring and the rest of the thing. You keep the interface constant and just redesign what's on the other side of it. That's a much more effective way of doing things. And so generally, architectural design is something that's settled upon at a very early stage, even when you're doing agile software development. Right? So you try to get that system design right from an early stage. The nice thing about it is that most software architectures can be described in terms of standard design patterns. Okay? Even though you're building something completely new, it's likely to have an architecture that matches with a lot of things that have gone before. Okay? So if you're designing a purchasing system, okay, you might be designing it for different customer needs and different sort of interfaces with different systems and that sort of thing, but there'll be some characteristics of it at the high level that are exactly the same as every other purchasing system that's gone before, or at least good ones. There might be some really badly designed ones that you don't want to replicate, but in general, there is a standard pattern that you will use. Right? So recognizing which pattern you should fit into and applying that right from the start saves a lot of time and effort, because you're not going to have to refactor at the architectural level down the track. Okay, so that's what software architecture is. Let's talk about who the architect is in terms of software. First of all, it tends to need to be a fairly senior, experienced software engineer. Just because it's hard to have the experience to recognise the patterns until you've worked with quite a few of them. Ideally, it's going to be somebody with people management skills because they're going to have to convince a lot of people that they've chosen the right design and discuss with them the implications of the design that they've chosen and that sort of thing. And they certainly have to have authority over the high-level design because that's what the architectural design is about. So what do they do in order to decide it? Well, first of all, they identify the concerns of the different stakeholders. Okay, to a certain extent, this should already have been done in the requirement specification and that sort of thing, but they might not have been involved in the requirement specification itself. They take the requirement specification that's been produced and then use what's been enumerated in that document to do their architectural design. Part of the reason why getting the requirement specification right is so important because lots of people use that document. Once they've identified all the concerns, they prioritise the concerns in the order of importance, right? And then think about what the logical influence on the system is going to be of those concerns. Okay, so there might be things like security or responsiveness or uptime, those sorts of things that the users have specified. You know, we can't have more than, I don't know, an hour's downtime per month, they might say. So what, at an architectural level, is that implication going to have? It might mean that you need to have redundancy in the system so that when one part of it fails, another part just takes over, that type of thing. So that's a design implication, an architectural design implication. You look at the physical context of the system. So are you having to work with existing hardware? Are you constrained by existing hardware? Do you have the freedom to choose new hardware configurations that are going to suit what you're going to do? The external constraints on the structure, things like who's going to have access to things, that type of thing. And then from that, all those things together, puts together the high-level architectural design. So let's talk a bit more about the different types of concerns that they deal with. First of all, we have the physical constraints. So a standalone system on a single computer or a distributed system. Almost everything these days is in some sense distributed. It's very unusual to be running standalone programs these days. Single user access or multi-user access? Okay, again, multi-user access these days is the default. But if you can write a system that's single user access, it makes life a lot easier because you have to do a lot less in terms of verification and that sort of thing. You don't have to worry about different people accessing different parts of the system. It makes it a whole lot more simple. Are you producing a single product, or is it a component in a larger system that's going to have to talk to other products? Okay, because if it's going to have to talk to other products, you're going to have to define those interfaces very carefully. So they're the physical constraints. Commercial constraints. So basically things that affect your contract. Is it what's known as a greenfield development, so starting from scratch, or brownfield development, where you've got something that already exists and you're either extending it or enhancing it or modifying it in some way? Obviously, if you're starting from scratch, you have a lot more freedom in your design. If you're having to integrate with existing products or change an existing product or something, you need to know what the architecture of that existing product is, or products that you're using in your system, so that you can develop your architecture on top of that. So has your client already committed to particular types of hardware or software or other sort of commercial constraints on them that are going to affect you? So do you have to use Windows PCs, for example? Or could you run a Linux system? that type of question. If you're looking at mobile devices, are you going to be using Android or iOS or both? That type of thing. And in terms of the in-house support, so is there any prior commitment to existing technology, such as like the web service that you're using or the type of database that you're using? If there's an existing team who are going to be supporting the thing that you are building within the company that you're going to give it to, and they're going to provide the in-house support, you want to be using technologies that they're familiar with in general, or otherwise you're going to have to train them up on new technologies, which is going to add to the cost of things. Okay, there might be a good reason for introducing new technologies, but if you do, you have to factor that into the cost of the contract that you're supplying to the customer. Then we have social constraints. Okay, so when we implement this system, who is going to gain from it and who's going to lose from it? Right? Are there certain people who are going to become stronger in some sense, either within the company or within the client's customer base or something like that? Are they going to gain from it? And are there people who are going to lose from it? Okay, if you're replacing a paper-based system, then there's a whole bunch of people who handle that paper-based system within the company who are going to be out of a job if you're not careful, assuming that's the only thing that they do. Or are you going to train them up to use this system, and you know, that sort of thing. So, you know, these are, in a sense, it's sort of an ethical type issue about how things are going to be. And that's related to the second point, the tensions. Whose job will be made easier or harder? Okay, so obviously if we're replacing a paper-based system, we're going to make the job of the people who file stuff away a lot easier, because they're not going to have all this paper to file. But those people might then be redeployed to do support for this system, and doing software support is a lot more difficult problem than filing papers away, so you make their job harder. So, you know, the type of thing like that. Security constraints are always a big concern. So we want confidentiality, particularly in distributed systems. We need to make sure that things are encrypted when we're sending them around. We don't want to keep multiple copies of data generally. There might be reasons to do it sometimes, but you need to be very, very careful when you do. We need authorization, so who has the rights to access which bits of data in the system. Generally, you have one sort of set of high-level administrators who can access everything, and then generally there's a tiered approach where you have lower-level administrators who get access to certain parts of the system, and general users who get access to very restricted parts of the system. We need to be very careful about the robustness and recovery, the protection of data. So what happens if a server fails? Have you got appropriate backups of the data? How often do you need to back up? How are the backups stored? That type of thing. If the system falls over, is it meant to be, you know, if part of the system fails, is that going to cause the whole system to fail, or is there some way that it can continue running without that particular subsystem for a short amount of time? Or do you shut everything down and restore from backup and then restart the system? And if so, how quickly does that need to be done? So these sorts of things need to be taken into consideration. And then logical constraints. So considerations such as, how much data are we going to be handling? If we're handling large amounts of data, the architectural design is going to be very different to if we're handling a trickle of data. Okay, because you've got to take into account both at the physical level and at the software level how you can process large volumes of data. At the physical level, you need to make sure that you've got appropriate network infrastructure in place. At the software level or logical level, you need to take into account how quickly you can process the data, how much data can you store, how much needs to be readily accessible, that type of thing. We need to consider how we're going to modularize the software. So even English speakers have trouble with English. So how are we going to break the software down into packages, right? Breaking it down into packages means that when we want to change something, we can focus on the particular package. So it makes a big difference to how quickly and easily we can update things and maintain things, because we can just focus on that particular area. If we've broken it down too far and we want to do an update, we might find ourselves dealing with a whole host of packages that need updating at the same time. If we've broken it down not enough, we might need to change one big package just for one small little update. So there's a balance to be made there. And how it's going to be packaged and deployed over different hardware. So imagine if you have a client-server architecture where the server is a PC or something larger somewhere, and all of the clients connect via handheld devices. How much processing gets done on the handheld device versus gets done on the server? How much data needs to be communicated between them? Those sorts of things are going to affect your architectural design. So when we're representing the architecture, generally it's just in the form of block diagrams. We don't have any fancy UML type things, although some people will choose to use high-level class diagrams to represent the individual components of the system. Sometimes these are criticised as being too abstract because they lack enough meaning about the items and the relationships between the items. But generally, when you're talking about the architecture, these are considered to be sufficient. And as I said, in many cases, there are templates available, and we're going to be looking at quite a few of them later in the lecture. The point of having these diagrams, the big point of having the diagrams, is that they can be a really good starting point for a discussion with various stakeholders. And it's another reason why architectural design is often done very early in the software development process. Sometimes even before the requirement specification is complete. Now that conflicts with what I said earlier, because I said you need to know what the stakeholders' concerns are before you can do your architectural design. But sometimes their concerns don't become apparent until you start proposing an architectural design. And they say, oh, but what about the security of data if we look at that, do it that way, right? So again, talking about an agile process, it can be an iterative type thing. So I've taken this diagram from the book because I think it's a very good summary of the types of questions that you have when you're looking at architectural design, in no particular order. So, is there a generic application architecture that can act as a template for the system that's being designed? So do we recognize it as, say, a purchasing type system, in which case we can use a general template? Is the software system going to be distributed across hardware or processors? Okay, generally hardware we're talking about, yeah. What patterns or styles might be used? It's related to this question over here. What strategy will be used to control the operation of the components in the system? Okay. Now when you talk about the control of the components, generally your architecture is going to have a lot of different modules in it. Are those modules, for example, going to be just a flow? So you start with this module, then that one, so you have a sort of linear processing? Or do you have lots of different things that happen in parallel, And in that case, do you have a central controller for all of them that decides when data is going to be transferred or something like that? Or do they speak directly to each other? Do you have a layered architecture where you have sort of highly secure stuff at the innermost layer and the user interface generally at the outer layer? These are all different types of control strategies that you're talking about. How should the architecture of the system be documented? Okay, in most cases, as I say, simple block diagrams are enough. But in some systems, for some clients, they might want something more detailed in terms of a UML type diagram. They might want something in natural language as well. So you need to negotiate that with your client. What architectural organisation is best for delivering the non-functional requirements of the system? So these are the things like security and downtime and response time and that type of thing. How will the structural components in the system be decomposed into subcomponents? Okay, so at a high level you've got a representation of the system, but within each of those modules they're going to get broken down further. You don't need to go all the way to the bottom with an architectural design. That's the key point. The detailed design fills in all of those details, but you need to give some sort of thought to what might happen within those modules, particularly when it is in terms of passing messages between the high-level modules. If you're going to have lots of things that need to communicate outside of a module, perhaps your architectural design isn't so great, because generally the idea with modularization is the idea that you have relatively little communication between the different modules. Okay, they're relatively independent. And what will be the fundamental approach used to structure the system? So what's the basic approach that you're going to use be? That might be driven by the customer's physical computing requirements, or it might be driven by an external regulator in terms of, the restrictions that you have been given in terms of either security or speed of processing or the response time to certain things that you have to adhere to. So there's going to be some fundamental thing that has set you on a particular path for your design. Now you don't have to answer every single one of these questions, but they're all good starting points for your architectural design, and you probably need to consider several of them, if not all of them. So I talked about the fact that we have lots of different patterns when it comes to architectural design. Right? We're rarely doing something that hasn't been done before. Okay? We're usually doing something that's not been done exactly before, because otherwise why are you doing it? But it's going to have some similarities to other systems. So here are some typical architectural patterns. First of all is a layered architecture, which I've already mentioned. Typical layered architecture separates the display of information, the processing of information, and the storage of information. Okay, so at the top level, you have the user interface, the display. Below that, there's a whole lot of functionality which processes the information either that the user imports or that they query from the lowest level, which is the database. The user doesn't have direct access to the database. That makes it more secure, because you put all your functionality in between to ensure that only the appropriate people get appropriate access to data. And the idea is that you visualize it mentally as horizontal layers with between each layer there is quite a lot of message passing, right? So there's strong coupling between the layers, but you never get the top level layer talking to the bottom level layer. It always goes through the middle layer. you can get more than 3 layers. Okay. One example of a 4 or 5 layer architecture actually is in one type of operating system design, where at the top level you have the user interface, again, the GUI. In the inside, at the very internal bit, are the kernel services. And the kernel services are the things that manipulate the hardware of the computer. So being able to access the disk, or drive the speakers, or put information on the screen. Then in between those layers, you have multiple levels where at each level it gets more and more specific, closer to the kernel level as you go inwards, or closer to the user interface as you go outwards. But you have to pass through each intermediate layer to get to the kernel level from the user interface. And at each layer there are checks and balances in place to make sure that only the appropriate requests are being accepted and that type of thing. Okay, and the reason that it's done in operating systems hardware is particularly on a multi-user system, you don't want 2 people to try to write to disk at the same time, because it will just fry the thing. Okay, you can't physically have 2 people doing the physical write to disk operation. It's a little bit different with solid state devices, because there you can access, they're more like memory than a old-fashioned hard disk. But even, like the audio, you might have, I know on my Mac, I can have 2 programs playing sound at the same time, right? So I could play music, and then I could have a Skype call that would be playing over the top of the music, for example. Now, some people might regard that as a bad thing. And certainly if you had a multi-user system, you wouldn't want one person to be playing music and then another person to try and play another music track at the same time. You might have something in place to say that only the person who's physically sitting at the computer can use the audio. But that would be one of those checks in the intermediate layers that would stop it from happening. Okay, partitioned architecture is basically this idea of a linear processing, possibly, but it could be a tree-like structure. Okay, so you might have a controller with several children, each of which does a separate thing, and they only pass messages back to the controller, backwards and forwards like that. The extreme form of it is a pipelined architecture where you do just have that one level from left to right. Input comes in, some sort of transformation, another type of transformation, another type of transformation, output. Typical example of a pipelined architecture would be something to do with language processing. Okay, so it hears the audio input, it translates that into phonemes, so the bits of sound, then it puts together the phonemes to form and recognize words, then it puts together the words to recognize sentences, and then finally has the text representation of the sound that went in. You could apply the same structure to do a translation type thing. Okay, so rather than finishing off with the text of the audio that came in, once you've got the text form of it, then apply another transformation to translate into another language, an output in the other language. You could go one step further, rather than outputting as text in the other language, go through the process of turning it back into sound. But in each stage, you're just doing one thing and passing it to the next stage. That's why it's a pipeline. And a transform center architecture. Again, the partitioned architecture is a kind of simple form of the transform center architecture, the tree type one I was talking about, where you have the one central controller with just a whole bunch of children. But you can take that to extremes, and is basically the idea that you have one central controller. The problem with this type of system, of course, is
that one subsystem fails, everything fails?
Not quite.
Centralization.
Centralization, yeah. So if one subsystem fails, it's okay so long as it's not the controller. Yeah. So there is a single point of failure, okay? And that in general is regarded as a bad thing in software systems. Okay, sometimes there are situations where it's unavoidable, but in most situations you would never have a single point of failure. So you would, at the very least, have a backup for the controller that was mirroring it as it operated, so that if it fell over, it could immediately take over control. Because that's the most simple solution to that problem. Not necessarily the best situation, but the most simple. So we talked about the characteristics of software systems, and so now the question is, well, how do they relate to those patterns that we've considered? If we're concerned with performance, one thing we want to do is to localize critical operations. Right? So anything that has to happen, we want to make sure that it doesn't need to talk to a whole lot of different subsystems, because if it is, then if any one of those subsystems fails, then the critical thing is going to fail. Whereas if you have it in a single module, there's less chance of the communication between the different things causing a problem. You know that it's isolated within that particular module. So we minimize communications, and a consequence of that is that we tend to use something that is less broken down. So not a lot of fine-grained components. Okay, so that's if performance is the issue. The more message passing that you have, the more likelihood of there's going something wrong with the messages, essentially. If security is a characteristic that we're particularly interested in, then a layered architecture is an optimal type, a pattern to use, with the critical assets in the hidden inner layers, so that they're a long way from any sort of external threat, and you have checking in place before they can get to that critical secure information. Safety is, in a sense, similar to performance, but you're just looking at the safety critical features and minimizing them to a small number of subsystems, and making sure that those subsystems particularly have the performance and etc. that is required. Okay, so you might not be concerned about performance as a whole, but for particular aspects of the system, the safety critical system, you need to have performance, security, most things as a very high priority when you're talking about safety. Availability generally means that we have redundant components and mechanisms for fault tolerance. So what's fault tolerance?
Fault happen, you can restore.
Yeah, so when something goes wrong, it doesn't break the system. Okay, so it might mean that you can restore data, or it might just mean that it recognizes a particular input which is inappropriate, and it either does error correction or it disregards it, or the way that it manages the fault tolerance is going to depend upon the system itself. It might be appropriate to discard data, or it might be appropriate to try and repair the data, or it might be appropriate to actually stop the system and say this needs fixing now. It's context dependent what fault tolerance means. And maintainability. Okay, so maintainability, in a sense, is directly counter to performance, because with maintainability, we're looking at very, very highly modularized system where we can focus on small parts of the subsystem and upgrade them or repair them or swap them with other ones very easily and quickly, right? And so we can replace certain parts of the subsystem. Of course, that leads to more message passing, which is counter to performance and sometimes safety. Okay, we also have different views of the architecture of a system. So a logical view basically just shows the key abstractions of the system in terms of objects or object classes. And this is why UML can be used here rather than just simple block diagrams, because we are basically talking about the high-level classes in the system. Of course, those high-level classes, when it comes to implementation, are going to be broken down into lots and lots and lots of smaller subclasses. Right? It's not anywhere near an implementation of the system yet, but it is an abstraction of the system in terms of classes. The process view is instead something which shows how at runtime it's composed of interacting processes, and it's about the communication between the different parts of the system and perhaps the timings that are important and things like that. So that's a different perspective of the architecture. The development view, which can be closely related to the logical view, but it's aimed at the software developers. Okay, so if you're talking to the software developers, you're probably going to have a slightly different perspective on the system breakdown to if you're talking to your client, for example. Probably a little bit more detailed is the biggest thing. And of course a physical view, because as we said, most of these systems are going to be distributed in some way, so you need to know what the physical hardware is going to be and how the software components are going to be distributed across that hardware. Okay, so it's not just a map of the hardware, it's a map of the hardware and which parts of the processing are going to happen where. So if you're doing a client-server type thing and somebody does a search on their mobile device, where does that search happen? Is it going to actually do the search on the device, or is it going to send the query to the server and do the search on the server? Most likely the second. Okay, because the data is on the server, it would be silly to try to retrieve all the data to the mobile device in order to perform the search. Because you'd have a huge flow of data coming back where really the user only wants the result of the search. Okay, so let's look at some more of the standard patterns in a little bit more detail. These examples are taken from the book, basically because they are the standard patterns, right? So it's not just the Somerville textbook that will have these patterns. Any textbook on software engineering will give you the same patterns because they are the standard patterns. Okay, so the first one I'm going to talk about is the model view controllers pattern. Okay, and this is the type of one that we're talking about where you have the user interface, which is the view, right? The model, which is the data, and the controller, which is the thing that talks between the two of them, essentially. So it separates the presentation and the interaction from the system data, and it's basically three logical components that interact with each other. But there's very little direct interaction between the view and the model, in fact. So the diagram and the conceptualization of it does have the linkage between them, but it's actually more like a layered architecture in many ways. Okay, so in the textbook, figure 6.6, which is this one, shows you the thing. Right. Excuse me. And essentially, any change to the data has to come via the controller. Right? When there is a change, it updates to the view automatically, so that doesn't have to go via the controller because it's assumed that the verification's already been done, and if the view had access to display that data in the first place, it should still have access to display that data. Right? A state query is asking about the state of the data. It's not changing the data, so it's allowed to go directly to the model. Right? So basically, these two arrows here, it does communicate directly between the view and the model, but it doesn't change the model, the data. Any data change has to come via the controller. It's typically used for database-backed website applications. Okay, so if you're building a website that lets the user manipulate data in a database somewhere, you would typically use this design pattern. Right? So it might be, say, an inventory management system would fit this pattern, where somebody is managing software, managing a storage facility where people can borrow items from the storage facility, so the tools that they want to do when they go out on a job, and keeps track of who's got the tools and that sort of thing. So they have an interface on their phone that lets them check if a tool is available, to borrow a tool if they want to, which keeps track of the database, which should represent what's in the warehouse and who's got what tools at any time. Right? So that would be one application, one type of database-backed website. There are lots of different types of database-backed websites. For example, a point-of-sale system could be viewed as a database-backed website as well. Okay. In an extreme case, Amazon, where when you look at an item on Amazon, it'll say, "Hurry, only 5 items left," more on the way. So it's keeping track of how many they have in stock, as well as what things they have for sale. A layered architecture, as I said, organising the system into layers with related functionality associated with each layer. I'll give you an example in a diagram in a minute of the system for sharing copyright documents held in different libraries. It's very commonly used when building new facilities on top of existing ones. Okay? The idea that the existing one is going to be a lower layer and you're just putting extra layers on top of it. But you could do it even for a greenfield type development where you were particularly concerned with security being at the bottom layer. The idea is that each layer is a modular section and you can replace that layer. Right? So if you want to change the way you do the authentication, for example, you just replace that layer, and so long as you keep the communication between the two layers the same, then it should just switch out and in nice and easily. Of course, the difficulty is getting that clean interface between the layers, because they do tend to be tightly coupled between each layer. There isn't just one point of communication, there are multiple points of communication, and the more points of communication that you have, the more difficult it is to write a clean interface between the layers. So here's this copyright example that I was talking about, and it's a 4-layer architecture. Right, so at the top level, you've got the browser-based user interface, the actual app that people have on their phone or something like that, or the web interface that they have on their desktop. You have configuration services, which are things like the group management, the application management, and the identity management. Right? And depending upon the person who logs in, they're going to get access to different levels of those services. Okay, so an administrator logs in, they'll get access to all of them. Your regular user logs in, they'll only get access to identity management and perhaps a certain level about the application management. So they'll be able to change some settings, but not all of them. Below that level, you've got the whole host of application services. We've got, it's basically a virtual learning environment and video services, newspaper. So it's kind of like what Mole should be like. Okay, Mole doesn't have a lot of this functionality, but other virtual learning environments would have all of these sorts of things where you don't have to log into different systems to get to your email, to get to your your Google Docs to do word processing, that sort of thing. They're all integrated into the same thing. And at the very bottom layer, you've got the utility services, which includes authentication. Why is it all the way down there?
First you need to log in to do anything else.
Yeah, you need to log in, but you're going to be logging in from this top layer here. Okay, and remember the communication only happens between layers. So in order to get from your login up here, you've got to pass through the configuration services and the application services and the utility services.
Maybe because authentication is stored in a database, so they want to match between the entries, like a username and password, which is stored already in the database.
Yeah, essentially yes. So basically, yes, it is going to have to pass through all these layers to go down to the bottom one, but you are going to have to go down to the secure data in order to do that authentication, because that's where the encrypted version of the password is stored and everything like that. That's why it happens down here. We don't want to be passing the sensitive information back up. Rather, we get the raw data and pass it down and do everything down here. Okay, so also down here you've got all of the storage things, the logging and monitoring, which is a standard thing that you need to do if you're worried about security, so that if you do have a data breach, you have some evidence of how it occurred and who caused it and that sort of thing. Search is down here for the same reason that authentication is, because all the data is down here. So you don't want to be passing all of the data up in order to do the search. You want to just get the query, bring it down, and then send the query result back. Okay, because we want to minimize the amount of information we're passing between the layers. It's much more efficient to just pass the query down and the result back than pass all the data up. Right? We have a repository pattern. Okay, so basically here that all of the data in a system is managed in a central repository that's accessible to all system components, but the components don't interact directly here, they only interact through the repository. Okay, so it's not like the previous example where the repository was at the bottom of the stack. It's that there are all these different things that talk to the repository. So again, I've got a diagram on the next slide which shows the example of the IDE, but if the main reason for doing this type of configuration is when you've got a system that's got large volumes of information that needs to be stored over an extended period, and you've got lots of different subsystems that want to access that data but don't need to talk to each other directly. Right? The advantage of it is that each of your components that's interacting with the data is completely independent and so very modular by default. And if you want to change one particular component, in one sense it only affects that one component, but it might change the way that data is managed or stored in the repository and so get propagated to the other components that way because of the data representation. But basically any change to a component is only going to affect the other components by virtue of the way it changes the database. Of course, again, we have this single point of failure issue. Right? So the repository becomes a single point of failure. So here is an example for an IDE, so an integrated development environment. Something like, I don't know, which, are you using one when you're doing your Java, or are you just using text editors?
Yeah.
Okay, all right. So you will move on to use an integrated development environment. There's various different ones available. There's IntelliJ, Eclipse, Xcode, you know, all of these things, which are not just for Java, they're generally for programming. Most of them will support lots of different programming languages. And they have different kind of features where you have, in some cases, UML editors, code generators. So there are some which will take a UML diagram and generate code from it. They generally generate really horrible code, but you can do it. You have the editors and different editors for different languages because they have different syntax highlighting for different languages and that sort of thing. Different indentation rules, different, you know, all sorts of things. You might have some sort of reporting attached to it that can tell you about, you know, the size of a particular project, how many lines of code there are, you know, how many test cases have been created. Have a design analyzer, a design translator. You can have testing suites. You can have all of these things, and they're all using the project repository, which will have not just one project typically, but a whole host of projects within it. Yeah? And so you can, for one project, it might be written in Python, so you use the Python editor. Another one's written in Java, you use the Java editor. Another one's written in C, you know, that type of thing. Now, again, to handle the single point of failure issue, you have a backup of your project repository. Right? It's very common these days to mirror your file system onto a Google Drive or something like that, so that's one way of doing it. It's not a perfect solution though, because sometimes if you have something go wrong on your local copy and you want to restore it from your Google Drive, as soon as you connect it to the network, the Google Drive gets updated to the trashed local copy, and so then that's a problem. Right? So that's not a proper solution to the single point of failure issue. A better example of the solution to the single point of failure is the way that cloud services work. So with cloud services, you have, and Google Drive is an example of one of them, your data is stored in a data center somewhere. Okay? And in fact, it's not necessarily stored in a data center somewhere. Different bits of your data are scattered all over the different data centers that Google has. Okay? If it's a university one, there are guarantees that that data center is situated within the European Union because for data protection regulations here we have to. Right? But if it's a non-university Google account, it could be anywhere in the world, that data center. And when it's scattered all over these different data centers, actually the way that cloud services work is that it keeps 3 copies of every piece of data. Right? And when you try to access your data, it's a bit random which of those 3 copies is accessed because it takes into account load balancing and that sort of thing. So if one data center has been heavily utilized at one point, it won't add your request to that data center. It will go to one of your other copies of your data and get it from somewhere that's been less heavily requested. Okay, so we get duplication of the data, and there are all sorts of mechanisms in place to ensure that when you update one bit of data, it gets updated in the other 2 bits at the same time, that when you delete a piece of data, the other copies get deleted, although interestingly they don't get deleted straight away. Okay, so that is worth knowing. If you're using cloud services and you delete something, there is no guarantee when that data actually disappears. So those of you concerned about security might be interested in that one. Anyway, but basically this idea is your project repository is duplicated. Another way of doing it is simply by using a RAID physical system, which basically means that you have multiple disks and it gets striped across the multiple disks, and if one disk fails, there is enough information across the others to restore the missing bit of data. Okay, so that's a more simple, localized situation for duplication. System backups can help, but generally they're only done once every 24 hours. So if you have a system crash, the best you've got is something that could be up to 24 hours old. It might be only an hour, or it might be only a minute old, but you don't know. Client-server pattern, very classic one these days, where you have a large processor or storage facility or something which is your server, and then a lot of less powerful clients is the typical type of pattern you're talking about here. So most of the functionality happens on the server, and the clients are just accessing the services provided on the server. Okay, again, we're talking conceptually about something that sounds like a single point of failure because you're talking about a server. Again, what tends to happen is you get multiple instances of the server, so that if one goes down, hopefully others are still available, and it happens seamlessly to the user. Again, an example on the next page. The principal example, of course, is that you've got things that are distributed across a network and, in some sense, always available. That's all I need to say, really. So here's an example of a film and video library. So we've got the internet. In this case, we actually have multiple servers for different subcomponents of the system. So it's not a single server, it's a client and servers architecture, right? And you could view this as a conceptualization of the thing, because in actual fact, you might have multiple instances of each of the servers, right? And so long as you've got multiple instances, then you're not going to have that single point of failure thing. But yeah, basically, the vast majority of the functionality of the system is on the servers, and the clients provide little more than a nice GUI to access that stuff. Okay? So it can be susceptible to network issues as well, and I'm sure that you have encountered situations like this where you've tried to access something remotely and it's been very slow on occasion, right? By shifting some of the processing from the servers to the clients, you can minimize that situation, but then you are relying upon them having appropriate processing power on the clients. And if you look around this classroom, pretty well everyone's got a phone on their desk, but the capabilities of the phones that you have will be widely varying. So some of you will have very, very high-end powerful phones that would be capable of doing a lot of processing, whereas others will have relatively cheap, inexpensive phones, which, I think there are good reasons for having these things. You don't care too much if you leave it on the bus, but but you can't do a lot of processing on it, right? And so the performance slowdown you would get by trying to do the processing of the phone would be worse than the performance slowdown that you would get by dealing with the network lag. So you've got to get the balance right. And that's part of about knowing what your customer base is. Like if you know that you're writing for a company, doing a client-server architecture for a company who are going to use it in-house only, and everyone is going to have an iPad, then you've got a lot more processing power to deal with than if you're writing for something for the general public where you've got no idea, and you've got to assume that some of your customers are going to have the lowest common denominator. Okay, so this is why you need to know who your stakeholders are and what their characteristics are when you're doing that architectural design. Last pattern, pipe and filter. Okay, so this is a slight variation on the pipeline pattern that I talked about before, where the processing flows from one to another for processing, but sometimes it gets split. Okay, so you filter data in one direction along the pipeline or the other, depending upon some characteristic of the data. Okay, so it's a generalized version of the pipeline. Generally used in data processing applications like the text processing that I talked about. Right? Another very similar example is a compiler. So interestingly, a compiler works in almost the same way as a text processing system. And we'll look in more detail at that in a minute. Pipelines are really easy to understand, okay? When I described to you the text processing system, you were all going, yeah, I can understand that, okay? It's straightforward. And many business processes actually are in a pipeline. So you get the invoice come in, and then you've got to process the invoice, and then, you go through the payment system. That's a pipeline. You do need to know in advance what your data output and input for each system is going to be. But you need to know what that interface is in a layered architecture. On any system you need to agree upon the transformation. And I guess the main disadvantage though is that you need to generally change the data representation between each stage. Okay, so there's a transformation of the data. Now sometimes, as in the language processing, that transformation is the desire of that part of the system. So you want to change from the sound that comes in into phonemes, and then that into words, and then, so you're wanting to do that transformation. So that is a really simple case of where you would want to have that transformation as part of the system. But when you're doing, say, a payment system for a company, doing that data transformation is sort of like an extra overhead on each step, because not only do you want data to go into the next part of the system, you also want data that's going to generate a report for that part of the system and that sort of thing. And so you're having that extra level of representation that is going to be needed there. So it can create extra overheads. Okay, it's a bit debatable about whether those overheads are things that you're going to have anyway, right? But okay, so here's a payment system. We have the invoices come in, you read the invoices, you work out which ones need payments. Where they have been paid, you issue receipts. If they haven't been paid, you issue reminders and so on. Okay, and this really, I guess, would be part of a larger system. You wouldn't have it in isolation. You would have it feeding into the inventory management and the sort of the ordering system and that sort of thing, so that you're keeping the inventory levels up to the desired levels based upon the history of orders and all sorts of things like that. So just one small component. Time for a break.